So good afternoon, everybody. Welcome to the Vergata Astrophysics seminar. Today we have the pleasure to host speaker Mathieu Remazeilles, who is a tenured researcher at the University of Cantabria in Santander. He earned his PhD at the Laboratoire de Physique Théorique in Orsay, and then he held a postdoctoral position at the APC in Paris, in Orsay again, and then at the University of Manchester before moving to Santander. And his main scientific interests are mainly related to the analysis of cosmic microwave background data, with specific expertise on disentangling astrophysical and cosmological components, which is indeed the main topic of this talk today, with the focus on CMB B-modes. So thank you, Mathieu, for having accepted our invitation, and the stage is yours.
Thank you very much for the nice introduction, and thanks a lot for inviting me to speak today at the University of Vergata. I would prefer in the future to be in front of everyone there, but anyway, this is the situation those last years, and we'll do with that. And thank you at least for giving me the opportunity to speak remotely. So yes, today I would like to discuss about the component separation problem for the search for primordial CMB B-modes, which is the signature of the primordial gravitational waves predicted by cosmic inflation. So I will start, I will try to be a bit pedagogical. I've been told that there are several students in the audience, so let's see what I can do here. I will start with a brief recap of the history of the picture of the universe. So at the beginning of time, at the Big Bang, we believe that intrinsic quantum fluctuations of the vacuum have been amplified to macroscopic scale by the ultra-rapid exponential expansion of the universe called cosmic inflation. So these fluctuations have been amplified to macroscopic scales to give birth to primordial density fluctuation, which are the seeds of the cosmic structure formed later in the universe. And these primordial density fluctuations come along with temperature fluctuations of the cosmic microwave background radiation, the CMB radiation, which is the first light emitted in the early universe 380,000 years after the Big Bang. Sorry. When the electron and photon decoupled, this is the first light released in the universe. And then by gravitational instability, the primordial density fluctuations have formed the first stars, then the first galaxy, and then the galaxy clusters, which are the largest structure in the universe. Okay, but the primordial density fluctuations are not the only prediction of inflation. This ultra-rapid and energetic expansion of the universe must have generated also primordial gravitational waves, which are kind of ripples or distortion of the space-time. And most of the effort of the CMB community today is to detect these try to detect these primordial gravitational waves predicted by inflation. And these primordial gravitational waves predicted by inflations have a signature in the CMB, anisotropies, which is under the form of a polarization pattern called B-mode polarization pattern. And here I put a question mark because this primary B-mode polarization pattern of the cosmic microwave background has not been detected yet. But it will be the footprint of the primordial gravitational waves of quantum origin predicted by inflation. So detecting the CMB B-mode signal will provide direct evidence of cosmic inflation in the early universe. And from this signal, if we are able to measure the angular power spectrum of the CMB B-mode signal, shown by the shaded gray area here, because we don't know yet at which amplitude is the signal. So this is shown here by this gray area here. The amplitude of the CMB B-mode power spectral would inform us on the energy scale of inflation. This amplitude is given by the tensor-to-scalar ratio, R, and directly relates to the energy scale of inflation. So you are probably aware that the CMB temperature anisotropy, the CMB E-mode polarizations have all been well measured by the Planck satellite and other experiments. For example, the CMB B-mode from lensing, this is a spurious B-mode signal due to gravitational lensing by large-scale structure which transform E-mode into B-mode. This spurious B-mode signal has also been measured by CMB experiment, but the primordial CMB B-mode signal due to gravitational waves has not been detected yet. And so several next generation post-Planck CMB experiments are being planned and aim at detecting CMB B-mode at a tensor-to-scalar ratio as low as R10⁻⁻3, basically. So we have ground-based CMB experiments like the Simon Observatory or CMBS4, which are telescopes in the ground, and space missions like Planck, but next generations. For example, Lightbird, which has been recently selected to be launched by the end of this decade, and PICO, which is a more futuristic proposal for a space mission. So they want to detect this signal, but this is quite challenging. The current state of the CMB B-mode observations is given by this figure from the BICEP-Keck collaboration. The lowest upper limit, the upper bound on CMB B-mode is currently fixed at tensor-scalar ratio below 3⁻⁻2 at 95% confidence limit. So the CMB B-mode has not been measured yet, but at least we know that it should be below this level, this upper bound. So going back to this picture of the universe, why it is challenging to measure CMB B-modes? Because we don't receive directly the CMB light. We have galactic foreground emission, which obscure significantly the cosmological signal. So when we observe the sky at sub-millimeter wavelengths, like this movie from Planck, what we see is mostly the emission from our own galaxy, the Milky Way. And so the CMB is just the background signal that we want to extract, and so we want to clean the foreground contamination. So galactic foregrounds are polarized mainly because of the underlying galactic magnetic fields. The drapery pattern that you can see on this picture from Planck shows, in fact, the orientation of the galactic magnetic field, which is orthogonal to the direction of the polarization when the magnetic field is projected on the plane of the sky. So synchrotron emission from our galaxy is mainly due to spiraling ultra-energetic cosmic rays electrons, which are spiraling in the around the galactic magnetic field and emit synchrotron radiation. Thermal dust is due to dust grains of nanometer sizes, which are hit by the UV light of the stars and which absorbs this light and re-emit in the infrared. And these are the main foreground emissions which obscure the CMB B-mode signal, and so synchrotron and thermal dust. So one can take the advantage of the fact that CMB and foregrounds have distinct spectral signature, distinct frequency dependence, in order to disentangle them in multi-frequency sky observations. So if you observe the sky into multi-frequency bands, then because of this distinct spectral signature, you should be able to disentangle CMB and foreground. This is the underlying principle of component separation. So on the left, this shows the frequency dependence of various components in intensity. But today we are interested in polarization. And in polarization, there are fewer foregrounds which are polarized, mainly synchrotron and thermal dust. And so you can see that synchrotron emissions dominate toward low frequency in the observations, while thermal dust dominates toward high frequencies. So this just shows multi-frequency sky observation from Planck. And so the idea of component separation is just solving an inverse problem. Given a set of multi-frequency observation, how to accurately disentangle the component of emissions contributing to this set of observations. So there have been several component separation methods which have been developed mainly for the Planck data analysis. And I can focus here on a very simple method called ILC for internal linear combination. So if you accept that the data, so the multi-frequency maps at a given frequency nu and in any direction of the sky n are the superposition of various components of emissions, so the CMB emission, of course, plus some foreground emissions and instrumental noise. You can model this data saying that the CMB fluctuations, the CMB anisotropy, scale across the frequency with a known spectrum, known frequency dependence, which for CMB is just a black body, or for CMB anisotropy is more precisely a temperature derivative of the black body, which in thermodynamic temperature units is achromatic. So we know the spectrum, the SED of the CMB. We want to recover the signal S, the temperature fluctuation or B-mode polarization anisotropy in the sky. And we want to minimize the foreground contamination and the noise in the data. So how we can do that? The ILC method solves this by forming a weighted linear combination of the multi-frequency data. So you assign some weight, W, to each frequency map, such that the variance of this linear combination is minimum, and such that the weights offer unit response to the SED of the component of interest, to the CMB SED here. Okay, if we expand the data implicitly are the superposition of these various components. So when you apply these weights, if we expand this expression, we get this expression, as you can see. And this second conditions means that this term is equal to 1. Therefore, your estimate S hat of the CMB fluctuations should recover the true CMB fluctuations without any multiplicative bias, multiplicative error, thanks to this constraint here. And you have an additive error, which is the projection of the residual foregrounds and noise into your recovered CMB map. But this additive error is minimized thanks to the first condition here. So this is the basic of the ILC. And there is an analytical solution for the ILC weights, which is given by this expression, so which only depends on the SED of the component of interest here of the CMB SED. C is just the covariance matrix of your data that you can compute by cross-correlating multi-frequency data. Okay, this is just a reminder of the simple component separation method. And Planck has widely used this ILC method. So it's called NILC because it's an ILC implemented on needlets, which are spherical wavelets. But this is the idea. Assigning weights, ILC weights to this multi-frequency map, you are able to reconstruct the temperature fluctuation of the CMB. The same for polarization data. You get a nice CMB polarization maps. But of course, for Planck, what you see here is mainly due to E-mode. This is E-mode which dominates the polarization data in Planck because B-modes have not been detected yet. Why it is more difficult to detect B-mode? Because this is a tiny polarization signal in the sky. It is not, oops, sorry. I don't see my screen. Okay. This is not, these fluctuations are about less than 50 nanokelvin temperature RMS fluctuation in the sky, basically. So very difficult to search for this signal. In addition, on top of the signal, the gravitational lensing effect by large-scale structure transform E-modes into spurious, noisy B-modes, which completely bury the primary CMB B-mode signal. And finally, on top of this, you have the dust and synchrotron foregrounds, which even bury even more the signal. And as you can see, galactic foregrounds, the galactic foreground power spectrum dominate the CMB B-mode signal at all angular scale in the sky. So what you actually see in the sky is a B-mode signal from our own galaxy. Foregrounds dominate the CMB B-mode at all angular scale and everywhere in the sky. But also, foregrounds, galactic foregrounds dominate the CMB B-mode at all frequency that you observed. And this is a Taft component separation problem because if you look at this picture taken from a Lightbird collaboration paper, you can see that this is the total foreground emission in solid black line. And this is where our signal stands for a tensor-to-scalar ratio of 10 to the minus 3. And this is if we remove 99% of the foreground contamination, we'll still have this level of residual contaminations, which is still above the primordial signal, the cosmological signal. So you understand that we will need to remove more than 99% of galactic foreground contamination, which is a huge challenge. So CMB B-mode versus foregrounds. We could think that polarization is less complex than intensity for component separation because we have fewer foregrounds. Not all foregrounds are polarized, fortunately, mainly just dust and synchrotron. But in fact, it's less complex, but it's more challenging because the signal is weaker. In our case, the CMB B-mode is much weaker than, for example, E-modes, CMB E-mode. So there is a huge dynamic range in amplitude between the foregrounds and the CMB B-mode signal, which means that component separation in this case will be much more sensitive to any slight mismodeling of the foregrounds. Much more sensitive compared to temperature component separation. B-mode component separation is more sensitive to any incorrect foreground modeling because of this huge amplitude discrepancy. This is something to keep in mind. Another aspect is that foregrounds cannot be avoided just by narrowing the frequency range of observations. In the past, we have heard several times that we could, for example, avoid synchrotron contaminations because this is a low frequency foregrounds just by observing at high frequency. But this is not true for B-modes. If you look at 300 gigahertz, for example, so quite high frequency for CMB experiments, you can see that the synchrotron emissions is of a similar order of magnitude compared to the CMB B-mode signal for R10 to the minus 2. So for R10 to the minus 3, at 300 gigahertz, the synchrotron is still dominating the signal. And also, another aspect is that at this frequency, you can see that the synchrotron has the same spectral shape than the CMB B-mode, which means that you have some spectral degeneracy, which means that if you want to break this spectral degeneracy, you have to observe on broad frequency range. Okay. So extended frequency range is important to break spectral degeneracies, and also because we cannot avoid in any case any foregrounds. They dominate over all the frequency range. So to come back to this issue that for B-mode component separation is much more sensitive to mismodeling of the foregrounds, I will try to show a pedagogical exercise which we perform in this paper with colleagues from Manchester and Oslo using the commander method, component separation method, which has also been widely used in Planck data analysis. This is a parametric fitting method. So in the case of the ILC, we say it's a blind method because there was no assumption about the foregrounds, no assumption at all, no parametrization of the foregrounds, only assumption about the spectrum of the CMB. Here, this is a parametric method where you, as we say, parametric means that we assume also, we make some assumption about the foreground spectral property in addition to the CMB. So this method were developed by Eriksen et al. And because it is making assumption about foregrounds, it is more prone to modeling errors. If you assume the wrong foreground models compared to what is actually in the data, you can get biased recovery of the signal, of the CMB B-mode signal, for example. But at least this kind of methods provide some feedback on the modeling on your foreground models so that you can correct your foregrounds until you get a decent model for your data. You can do that because you can get maps from Commander, maps of the chi-square statistics, which is just the mismatch between your data and the model you fit squared divided by the noise you have in each frequency and each pixel. So in this paper, we did some exercise where we have some complex simulated data, which include the CMB B-mode signal, but also synchrotron emission with some curvature of the synchrotron, some curvature. So it's not a strict power law for synchrotron emission, but a curved power law with a curvature term here. We assume two components of dust emission. We assume some polarization of anomalous microwave emission, slight polarization of anomalous microwave emission, etc. And we try to fit either the correct model, either the model that matches the data, but we also try to fit a simpler model. So we made this exercise of deliberately assuming a mismatch between the foreground model and the actual data, the simulated data. So again, in our model, we assume a power law for synchrotron and a modified black body for thermal dust, but the actual data are more complex with synchrotron curvature, extra dust component, and extra AME polarization. And here are the results. You can see the impact on the recovered distribution of the tensor-to-scalar ratio. So on the left, this is when you fit the correct foreground model to the data. And on the right, this is the impact on R when you omit, for example, the synchrotron curvature. You can see that all these experiments, which were proposal at that time, Core, Lightbird, Pixie, Epic, etc., all the experiments start to get biased by omitting just a synchrotron curvature in the model. If you neglect AME polarization, again, you get biased recovery of R. Some of the experiments are more sensitive to this omission. For example, Epic here shown because this proposal of CMB experiment was supposed to observe at quite low frequencies and also high frequency, but especially at very low frequency where IME, so at low frequency which are sensitive to AME emissions. So the impact is more important. And now if you mismodel two dust modified black bodies as a single modified black body, you can see that all experiments get biased at more than 3 sigma. So the CMB B-mode component separation is highly sensitive to foreground mismodeling. But further than that, if you look at the chi-square, which can be an indicator of to get evidence for incorrect foreground models in your analysis, you can see, so if you first fit the correct dust model, you get unbiased value of R. So the fiducial value of R in this exercise was 5 × 10⁻², so unbiased value of R, and the chi-square, the reduced chi-square, was close to 1, so you have a very good fit when you fit the correct model, as expected, of course. When you fit the incorrect dust model, you get biased value of R, but interestingly, some of the experiments does not show high chi-square due to incorrect dust modeling. In fact, only the experiment which observed at very high frequency, like these two, PRISM, epoch, show a high chi-square value and thus indicates that you fit the incorrect dust model. So this is an important point, an important aspect I want to insist here. It's easy to fool yourself with future data because CMB experiments with maximum frequency below 300 GHz from these results get a chi-square, reduced chi-square close to 1 despite a biased value of the tensor-scalar ratio. This is because you get a decent fit of the total sky emissions, which does not mean that you correctly fit for individual components. You may overfit for one, underfit from the others, and still get a decent fit of the total emission. Say differently, is that on narrow frequency range, you get spectral degeneracies in your components, in your models. So without frequency above 300 GHz, it will be difficult to get chi-square evidence for incorrect foreground modeling and bias detection of R. So that's why it's important to go to space also, because in space you can you have not limited by atmospheric absorption, and you can observe at high frequency above 300 GHz. So observing at high frequency not only help to clean foregrounds, but also to get evidence for incorrect foreground modeling and bias detection of R, because we will have to trust a detection. We will detect a signal, of course, with any CMB experiment, but you have to trust that it is CMB B-mode, primary CMB B-mode, and not foreground B-modes. Another aspect, another challenge or subtleties or issues that we'll have to take into consideration is about the fact that our current parametrization of the foregrounds may be actually obsolete. So this is a bit provocative, but you have seen this picture many times in Planck paper, etc. But this description of synchrotron and thermal dust as a power law and a modified black body for thermal dust is a good description at sensitivity level required for temperature analysis. For CMB B-modes, probably this classic picture is now obsolete. And I will tell you why. First, because the instrument makes spectral distortion to the baseline foreground SED, to this SED. For example, when we have a CMB imager, we don't observe in 3 dimensions, but just in 2D, a projection in a 2D map of all the contribution along the line of sight. So when you observe in each single pixel, you integrate, in fact, multiple contributions of the thermal dust emission, which is a 3D emission. It's at redshift 0, but there is some extension along the line of sight. And so this averaging of multiple clouds of thermal dust emissions with various spectral property, with different temperature and different spectral indices, you are in fact effectively averaging along the line of sight multiple modified black body components, and the sum of modified black bodies is no longer a modified black body shape. So the effective SCD of your thermal dust emissions is slightly different than a modified black body. This tiny difference was not a big deal for temperature analysis. They can be a big deal for CMB B-modes because the signal is weaker. Another kind of spectral distortion of the foreground SCD is not only averaging along the line of sight, but also averaging between the line of sight inside the beam of the instrument. For example, suppose that you observe at high frequency with high resolution some synchrotron emissions. Even if your synchrotron emissions in each line of sight can be described by a power law with some spectral index, and this spectral index vary from line of sight to line of sight. When you observe at lower resolution, generally you observe when you observe at low frequency, generally you observe with a larger beam, and so you effectively inside the beam you effectively average several power laws with different spectral indices, and the average of different power laws with different index is no longer a strict power law, but a curved power law, with the curvature term simply given by the variance of the spectral index inside your beam, the variance or the second order moment of the spectral index. So you may have a power law emission for synchrotron at high frequency, but a curved power law at lower frequency, at lower resolution. And so this is a kind of decorrelation of the synchrotron emission across the frequencies. So if you don't take into account this spectral distortion of the foreground SCD, you may mismodel your foregrounds. And as we have seen before, slide mismodeling can create large biases on R, on the tensor-scalar ratio. So this is the summary of the spectral distortion of the foreground SCD, which arises from line of sight averaging and averaging between line of sight inside the beam. This creates decorrelation across frequency, and so this augments the list of expected foreground parameters. It's no longer a modified black body, but something more complex. It's no longer a power law, but something more complex with some curvature, etc. And even if these distortions, these spectral distortions are second order effect compared to foreground, so are small compared to the baseline foreground emission, this second order correction to foregrounds will be much larger compared to the CMB B-modes, or of similar magnitude. So small effects compared to foregrounds, of course, but compared to CMB B-mode, these spectral distortions are significant. So we have to take into account this aspect for unbiased recovery of CMB B-modes. So we may think of extending current parametrization of the foreground. So if you start from the leading order SCD of the foreground, assuming synchrotron is close to a power law, thermal dust is close to a modified black body, and so the intensity is the amplitude of these components times this baseline SCD. This is a zeroth order approximation, let's say, of the foregrounds, but we may want to extend these parametrizations by performing a Taylor expansion or moment expansion of the foreground emissions beyond the leading order SCD. So you perform this Taylor expansion around some average spectral parameter, and by doing this expansion, in fact, you generate extra components. So line of sight averaging effect and averaging effect between line of sight inside the beam create this spectral distortion to the baseline SCD, and this spectral distortion can be modeled as these extra terms, extra components through this Taylor expansion. These are really extra component of emissions, not necessarily physical component of emission, but really moment components which fluctuate across the sky. And this also highlights new SCDs for each of these moments. So this is the first order moment, the second order moment. And here I just plotted the SCD for synchrotron moments and dust moments for the zeroth order and first order moments to give you an idea. And the expression, for example, the zeroth order moment for synchrotron is the power law with spectral index. And just to give you an idea of the SCD shape for the first order moment and second order moment, they are modified like that if you perform this Taylor expansion. The same for dust, modified black body, and higher order terms, higher order moments here are shown. You can find the details of this expression in this paper. And so now the idea is how to incorporate this moment expansion technique into component separation. And the idea I developed in this paper last year is to augment the classic ILC method to incorporate extra constraints to deproject these foreground moments. So you remember the routine ILC method, the standard ILC method. You perform a linear combination of the data, and you just assume these constraints that the weights offer unit response to the SCD of the CMB. Here I show the results of the classic ILC method for Lightbird on simulation of the Lightbird space mission. This is performed full sky, but here I highlight on the BICEP 2 area in the sky, a clean area of the sky, what is the residual foreground contamination after component separation by the ILC. So you can compute this projected foreground contamination in your CMB B-mode maps because it is a simulation. So you just have to apply these weights to the pure input foreground of your simulation, and you get an idea of the residual foreground contamination in your CMB map. Of course, this is because this is simulation. It's just for illustrative purpose. You cannot do that on real data. So this just to show you what is the level of foreground contamination in the recovered CMB B-mode map when you perform a normal ILC component separation for Lightbird. So you see the fluctuation here, and you see the power spectrum of this residual foreground contamination for the ILC, for needlet ILC, for NILC in red here. And you can see how it compares to the theoretical CMB B-mode signal shown by the gray shaded area here, which is the CMB B-mode signal between R10 to the minus 2 and R10 to the minus 3. So residual foreground contamination for needlet ILC will be larger compared to the CMB B-mode at R10 to the minus 3. And so now, can we augment this needlet ILC method by adding some extra nulling constraints against the SCD of the zeroth order moment first of dust and synchrotron? And you can see that by adding extra constraints, by using a more constrained version of the needlet ILC to deproject the spectral moment of the foregrounds arising from line of sight averaging, by adding these extra constraints, we progressively erase the residual foreground contaminations. And if I add more and more constraints, you can see in this movie that we progressively fully erase, almost fully, erase the residual foreground contamination in the recovered CMB B-mode map. And the residual foreground power spectrum is very low, when you add constraints, nulling constraints against zeroth order and first order moment of dust and synchrotron. We can look at another figure of merit. If you take the 1-point statistic of your residual foreground maps for the normal needlet ILC and for more constrained version of the ILC using moment deprojections, you can see that by deprojecting more and more foreground moments, we significantly reduce the non-Gaussian foreground contamination in the recovered CMB B-mode map, with the blue showing the residual foreground contamination for the most constrained version of the ILC with first and with zeroth and first order moment deprojected. So it reduces the overall contamination, even the skewness of the residual foreground contamination. And of course, there is a compromise in this strategy, in this component separation strategy, because we add more and more constraints to the ILC, because we augment the volume of the parameter space by putting constraints on higher order moment of the foregrounds. Of course, we reduce the residual foreground contamination on the left, but as a trade-off, we increase the residual noise, the statistical noise in the recovered CMB B-mode signal. So there is a trade-off, but there is somewhere a sweet spot. And this is what we will see. So from the recovered CMB B-mode map, we can compute power spectra. And from the recovered CMB B-mode power spectra, we can perform a likelihood estimation of the tensor-scalar ratio, which I will finish on this. So this is a recovered tensor-scalar ratio value. So maybe forget about all these colors. This is for different level of delancing. But here we focus on foreground cleaning, so forget about delancing and just look at the black line, let's say. This is the recovered tensor-scalar ratio value after component separation by the standard needlet ILC method. The fiducial value of R in the simulated data is R equals 0, so no primordial CMB B-mode. So, but you can see that the normal needlet ILC method, the standard needlet ILC method, recover a biased value of R, a non-zero value of R. So you can see that it peaks around 3 × 10⁻³ . So this, what you see actually is the tensor-scalar ratio of the residual foreground contamination. But now, if we perform this more constrained version of the ILC, with a moment deprojection, you can see in the dashed line that we progressively erase residual foreground biases. This is with constraints on a zeroth order moment of dust and synchrotron. But if I add first order moments, these additional constraints enables to erase even more the residual foreground bias. And if you add even more constraints against the dust temperature moments, you are completely consistent with R equals 0, but now you start to pay a large noise penalty because you cannot add as many constraints as you want given the limited number of available frequencies of light bulb. So the sweet spot basically is here because we are able, by deprojecting the moment of the foregrounds with this constrained ILC method, we are able to remove the foreground bias, recover R equals 0 without any bias, without paying much noise penalty compared to the pure blind NILC method. I don't know if I am in advance or not, but I will conclude now. So in this talk, I try to show different subtleties or issues we'll face for the detection of CMB B-modes and a strategy to overcome these challenges. So what I have shown is that the primary CMB B-mode signal is largely dominated by galactic foreground emissions at all frequency, at any angular scale, and everywhere in the sky. Because of that, it is like if you were trying to search for noise in your data instead of signal in your data. And because this signal is very low compared to the signal to noise, or the signal to foreground ratio is very low, it's preferable, it's better to work directly on maps than in power spectrum, because you need information beyond just the 2-point statistics to perform a decent component separation. The exact spectral property of the polarized foregrounds are still poorly known, or not known actually, at the sensitivity levels of B-modes. In addition, there is this additional complexity that our knowledge of the baseline foreground SCD could be distorted due to averaging effect along the line of sight and between line of sight. So this further complicates the picture. B-mode component separation much more sensitive to foreground mismodeling due to huge amplitude range between foregrounds and CMB B-modes. And we have shown that moment expansion of the foreground and deprojection by constrained ILC method provides an interesting avenue to overcome this challenge for B-modes. And also that extended frequency coverage, broad frequency coverage, is recommended not only to help foreground cleaning, but most importantly, to get evidence for incorrect foreground modeling and biased detection of R. So to trust your detection, you need some red flags, and these red flags are given by extreme frequency, low and high frequencies. Thank you for your attention.